Chris, it's over to you.
All right. Good morning, everybody. Welcome to our session for today. I'm glad you're all here. Thank you for showing up on a Saturday. I know that Saturday is your time. I get that entirely. And I appreciate that you all wanted to come in and spend a little time talking about physics or reviewing physics. So what we're going to do today is I'm going to show you PowerPoint, but I'm going to ask you lots of questions, okay? And so what I'd like for you to do is the same thing I ask for my students is when we go through some of these questions, I'm going to ask you to type your answer in the chat, okay? Don't be afraid to type your answer in the chat. This is one of the things about science that's makes it a little bit unique other than other subjects. We progress and we learn things when we communicate it with other people. The thing about science is that we most of the time never know the correct answer. And so we're always trying to get better. And so or better understanding. And so when I ask you a question, I want you to just type your answer in the chat, the best that you think that you know. And when you're in class, you need to compare your answers with other people. We call this cheating. I mean, collaboration, right? This is collaboration in the real world. And so that's how science progresses. So please put your answers in the chat. All right, so here we go. We're going to talk about how things move, talking about position, velocity, acceleration, which the catch-all name for all that is kinematics. So here's our first one. A student is shown a position versus time graph for two objects and is asked to describe the motion of the two objects. The student responds, object B is moving faster because it has a steeper slope. What about the student's claim is correct and what is incorrect? And explain. So what I'd like for you to do is, could you please type in the chat whether you think this statement is correct or not? All right, we got one response. Come on, everybody, you can do it. Just type your best guess in the chat. Ooh, we have correct, incorrect.
Right.
All right, so it looks like correct is coming in more and more. All right, so here's my question. How do we find, the statement is that the object's moving faster. How do we find how fast an object is moving on this type of graph? All right, so here's the deal. Every time that you see a graph on the physics exam or any kind of physics situation, always, before you go anywhere, is to look at the axis on the graph. Look at the title if there is one. Most of the time on the test, there's no title, but there'll be axis on the graph, and the axis on the graph will tell you what it is. So like this is a position time graph, and a position time graph tells you where an object's located at any time. So in order to get the velocity information, we have to find the slope. So it turns out that their answer is correct. The velocity is found from the slope of a position time graph, and B is steeper than A, therefore B is faster, okay? This is the kind of the way that they would expect you to justify your answer on the test. You tell them whether you answer the question first, okay? And then you back it up with the physics of the situation. So like, this is how we find velocity on this graph, all right? Okay, here's our next one. So I'm just warming your brain up before we get to some of the harder ones. Each graph below shows a position of an object as a function of time. There are 4 graphs. Rank the magnitude of the displacement during the time interval from 0 to 4 seconds. Okay, so I'd like for you to type your answer in the chat by doing something like A is greater than B is greater than C, like that. And if any of them are equal, just put like A is greater than B equal to C. Does that make sense? So type it in as an equation.
I just typed in a sample, but that's not the right answer, I don't think. So, but just you can type in a response a little bit in that same format, and it doesn't have to be A, B, C, D, obviously. I'm finding it helpful to have a pencil and piece of paper next to me.
Yeah, you may need paper and pencil. All right, very good. So when you take or when you look at any of these questions, like on the AP test, the key thing is to look at the wording, because the wording, it's written in scientific language instead of real English. So all these words have some meaning associated with them. So when it says rank, okay, you're going from highest to lowest. And then magnitude means we don't care whether it's positive or negative. So C has a negative slope or negative displacement, I should say, but they don't care because they just want the magnitude, right? So very good. So the answer would be, oops, C greater than B, greater than A, and A and D are the same. And we find displacement on this graph by just subtracting the initial and final positions. And there we go. Excellent. We're doing good.
Before you go on, can you go back just a second?
Sure.
If the question had asked about the distance traveled, then D would be the greatest, wouldn't it?
That's correct. So if this had asked for the distance, then D would be the greatest because the distance would be 8 forward and then 8 backwards. Think about if you were in a car and you drove 8 miles east and then 8 miles west, it would read 16. Okay.
And that would be kind of similarly, if you were to take the average velocity of D would be 0, but the average speed would be 4 meters per second. Is that correct?
That's correct.
And that's, so I think that's important for people to read and understand that velocity has a component with it. But
yeah, so please be careful to watch for the wording of what they ask for, because they'll ask sometimes for speed and sometimes they'll ask for velocity. Okay. Okay, in each figure below, the car's velocity is shown before and after a short time interval. So like in A, this is the before speed and this is the after speed. Rank the magnitude of the change in velocity during the time interval. Okay, type your answer in the chat.
You guys are doing that so well. You know how to, I know you're all smart people. You know how to figure that out.
All right, the key point we're getting across here is the idea of direction, and it's a vector. And so C, you are going forward, and then you're going backwards. So if you take the final velocity minus the initial velocity, you would get a net change of -20, okay? But they want the magnitude, so the magnitude would be a change of 20 meters per second. So C is the greatest. Both A and D increase by, well, see, A increases by 10, D decreases by 10, but we're looking at magnitudes. They have the same change in magnitude, okay? All right, so our answer is C greater than A and B and D are all the same because A speeds up 10, B slows down 10, D slows down 10, and for magnitude, that's all the same. Okay, remember magnitude's like absolute value. So you look at how much the change is, and then you wipe out whether it's positive or negative. All right? Okay. The graph below show the velocity of two objects during the same time interval. Okay? Now, for the 6-second time interval shown, all the way across from beginning to end, is the displacement of object 1 in the upper graph greater than, less than, or the same as object 2? So the key question is look at our graph. How do I find displacement? Ooh, we got a vote already of greater than. How about this? Type in the chat, how do we find displacement on a velocity time graph? Oh, somebody already
There you
wrote it in.
go.
Matt,
Okay.
very good. Because it's the area under the graph. So if you look at the graph, you'll see that you have an area here. If we just count the blocks, that's 1, 2, 3, 4. And you count the blocks over here, 1, 2, 3. And we can just count the blocks since they have the same axis. All right? Awesome. You're doing fantastic. All right. See if you're paying attention. The student is shown a velocity time graph for two objects and is asked to decide which of the objects is moving faster. The student responds, B is moving faster because it has a steeper slope. Is the statement correct or incorrect? If there's something wrong with it, correct the statement. If it's correct, explain why it's correct. Outstanding. Physics students are the best. All right. So when you look at this, very first thing, always look at the axis on the graph. So this is a velocity time graph. Okay, so how do we find velocity, or which one's going faster on a velocity time graph? Well, you just read the graph. So if you look at the graph A, you'll notice it has, at the beginning of time here, it's moving faster than B because it's higher up. And then at no point does B ever get faster than A. They're both accelerating. So the slope on this graph is the acceleration. Yeah. So the deal is it's easy to get confused, okay? And the questions on the AP test, they're multi-layered. So here's how they'll even make this worse on the AP test. They'll give you this graph, and then they'll ask you, there are two forces acting on similar objects of the same mass, okay? So object A and object B have the same mass, okay? Which one is being pushed by the largest force or the largest net force, okay? So you've got to think about, okay, this is a velocity time graph. How is this at all related to forces? Well, we would know that forces are directly proportional to the acceleration, right? F equals ma. So we could say, oh, so I could look at the slope. So B has a larger slope than A. Since B has a larger slope than A, the net force on B must be greater than the net force on A, since they have the same mass, okay? So they'll ask questions like that are like a couple layers deep. So it's easy to get them mixed up. Okay, so here we go. Start now that our brains are warmed up. The figure at the right shows the vertical velocity of an elevator as a function of time. Okay, so this is an elevator. Question A, describe the motion of the elevator. So just put it in words. What's going on in this elevator? All right, Will, pretty good. All right. Okay, you're on the right track. First thing is to look at the axis. This is the vertical velocity versus time. So the initial velocity of the elevator is 0. So it starts at rest, like it would when you get on an elevator. And then it goes upward. And in this first section, okay, what's it doing in this first section from 0 to 8? 0 to 8 seconds. A lot of you said it's moving up, but be more specific. There you go. That's the word I'm looking for. So we want to use our physics terminology to describe it, okay? So what we want to avoid on the physics test when we describe things is to use, first of all, pronouns. Like we wouldn't want to say it goes up. We would want to be more specific. We would say the elevator is what? Accelerating, right? It's accelerating in the positive or upward direction, right? So make sure that when you're describing motion that you describe the initial position, if you know it, describe the velocity, whether the velocity is constant or not, and if it's accelerating and which way. So like which way is it moving with a velocity, and is the acceleration making it speed up or slow down? Okay, those sorts of things is what we're looking for. Okay, so in this first section, the elevator accelerates upward, okay, until it reaches its cruise velocity. And its cruise velocity is 14 meters per second. So then it keeps going up for another, well, up until about 18 seconds. And then, okay, here's the thing. In this back section over here, from 20 to 25, is it still going up? Yeah. It is, right? Oh, somebody raised their hand. Did you have a question? If so, just pipe it out. Because we got a small group. Hey, and by the way, let's just say that we're typing our answers in the chat just so we don't talk over each other. But if at some point, I didn't mean to, oh, no worries, no worries. If at any point you have a question, like something's confusing, just unmute yourself and ask the question, okay? All right, so yeah, it's still going up, but it's slowing down to a stop. Okay, so now, they'll ask you to do this a lot on the test. This is the technical name for this is called changing a representation. So you got this representation of the velocity versus time. You described its motion. That's a different way to represent or model what's going on. And now I'm going to ask you to do a couple of different ones. Can you sketch the acceleration versus time graph that goes with this? And can you sketch the position versus time graph that goes with this? Okay. The acceleration versus time one is easier, I think. And the position versus time one will be a little harder. Okay, see if you can sketch them. I'll give you a little bit of time for this. All right. Okay, I'm going to show you what what they would kind of look like. All right, so they should look something like this. Now, a couple of things. Whenever you're sketching a graph, when it says sketch, okay, they don't mean plotting points. So when they say plot, that would be like if you have lab data. And if you have lab data, then you're going to have to label the axis with units and everything. And then you're going to have to plot your points, make sure your dots are visible. Okay. And then if you're probably going to have to draw a best fit line through it. Okay. But when they say sketch, they're just looking for the basic features of it. So on an acceleration time graph, an acceleration time, then what they're looking for is, do you see that you have a constant acceleration for the first 8 seconds? And they might ask you to label it. It's always good to label it if you have numbers. If there are no numbers, then you would just show that it's flat. Okay. And then there's a section over here where there's no acceleration in the middle because the slope is 0. And then over here at the end, you can see that you have the acceleration that is negative. Now, the one thing to note is that this negative acceleration is bigger than the positive acceleration we started with. This is a steeper negative slope than this is positive. So they'd expect this one to be farther away from the axis, from the horizontal axis, all right? And you can label it if you want. And you notice you have a curved section in here. That's really a calculus thing. That's a little bit above our pay grade. But if they show you something like that, then they'll expect you to just draw a transition. It started at 8, ended at 10, and it started at 18 and ended at 20. Okay? They're not going to be real particular about the transition, just that you know that it moves from one to the other. Okay? And then this one is much harder, I think. So the object is accelerating for the first 8 seconds. It has a positive acceleration. That means the displacement, or our position versus time graph, will be a parabola upward. Okay? And so we're starting with a parabola upward. They didn't tell us where we started, so I just put it at 0. Okay, I just made that assumption. So I have a parabolic upward slope, and then on the back end, it's a negative acceleration, so I should have a downward parabola. Okay, you see that this is part of a large parabola over here, right? And in the middle, we have a constant velocity, which is linear on a position time graph. And there'll be some sort of transition. I just drew a kind of dotted line in between there to let you know that, there's going to be some transition in here. They're not going to worry about that. What they're going to look for is, can you draw a parabola here? Can you draw a parabola over here, pointing in the correct direction? And did you connect it with a line? Now, on the AP test, if you can't draw this properly, let me show you. If you're in a hurry and you're kind of wigged out about the whole test, and you go like this, because this happened to some of my students. They go, hey, I know it's a parabola, and then they go like this, and then they go parabola, okay? Now, this should be a smooth transition, okay? So if you can't draw it correctly with a nice smooth transition, then literally just write in words. Just write smooth transition, all right? So if you get stuck on something, like you're trying to draw something and you're having trouble drawing it, this is not an art test, okay? So you can do this if you need. Just like, this is what I'm trying to draw. Like on sometimes on a free body diagram, students will draw their forces, and they're like, I want them to be the same size, and you can just mark them that they're the same size. So you can write same size. Okay, just clarify. That's okay. Because the people that grade these tests, they're very nice people. They want you to be successful, but they can't give you points unless they understand what you're saying or doing. Okay, so just explain what you're doing. Try your best to use the unnatural terminology of physics language. Okay, so try to use physics words and not like what you would use if you were on Twitter. Okay. All right. The last question on here is, how would you estimate the total displacement? of the elevator over the entire time? Well, just remember that the displacement would be the area under the graph. And so that's why usually they don't have any curvy sections for us, so we can easily find the area. But if they have a curvy section, just say, I would estimate the area under the graph, okay? You know, like you'd say by counting up the squares and seeing what the size of each square is. Like each one of these rectangles here is a 2 by 2. So each one of these would equal 4. So if you have a curvy line, that's how you would estimate the displacement, okay? All right. So here are 2 questions. Students track the motion of a car moving horizontally from left to right by placing a dot at the position of the front of the car every 2 seconds. They produce the preceding motion diagram. Which of the following velocity time graphs is consistent with the motion diagram? Okay, that's our first one. And our second one is the physics student releases a lab cart from the top of an incline as shown in the figure. The teacher asks the students to predict what the position time graph for the horizontal motion of the graph would look like. 4 students give these answers. Which one is the most accurate? Okay, so I'd like for you to type in the chat, what's the answer to the one on the left and one on the right? All right, the consensus seems to be on the left. It's looks like most people are saying A, few are saying B. And on the one on the right, we have, looks like people are saying A and B. Or we can't decide whether it's A or B. All right, so let's find out. So this one on the left, this is a dot diagram or a motion diagram, okay? So the dot, the spacing of the dots tells us every 2 seconds where it's located. So we can see in this middle section, they're spaced evenly, so it has a constant velocity, okay? We can see at the very end, they're all spaced evenly. So it has a constant velocity, but the velocity at the end is slower than the velocity in the middle. And then in the front end, we can see that it's accelerating. So it looks like it's accelerating to a high constant velocity and then slowing down with a negative acceleration to a low or slow constant velocity. All right. So how do we find velocity in a velocity time graph? Well, we just plot it, right? So acceleration would be a constant slope up, and then we have a constant velocity in the middle and then a constant velocity at the end. All right, so it looks like it should be A, okay? And then this other one, we're looking for, okay, look at the motion. What's this cart gonna do? It's going to accelerate down, and then it's gonna move, assuming we have little friction, it's gonna move at a constant velocity, right? So what does acceleration look like? And what does constant velocity look like on a position time graph? Okay. So how do we find, on a position time graph, we find velocity with the slope, right? And then things that are accelerating, they'll have a curvy parabolic up if they have a constant positive velocity, parabolic down if they have a constant negative velocity. So it looks like A is our correct answer. So we are accelerating up, accelerating to the right, sorry. And then we have a constant velocity. Okay. All right, let's stay on this one since we're here. If this one on the right, if they'd have asked for a velocity time graph, how do we show acceleration and then constant velocity?
I'm glad you're doing this, Chris. This is exactly what I did. I got that wrong because I assume you still wanted the velocity. I did not.
Yes, and that's why I put them together, because it's so easy to just, not pay attention to the graph axis and just, you're on the right track. Everything is correct. You're just answering it for the wrong type of graph. So a velocity time graph, excuse me, acceleration would be like a slope, right? And then a constant velocity would be flat. So if this was a velocity time graphs, it would look more like C, right? It speeds up and then it goes constant velocity. All right. And this one right here, if you did a position time graph, it would look like B. It accelerates to a constant velocity, then it slows down to a slower constant velocity. It goes next T graph. And actually C right here is what the acceleration versus time graph would look like. Okay? Positive acceleration, negative acceleration, and constant velocity in the middle on these other two. All right. Okay. High school student, much like yourselves, releases a ball from the edge of different cliffs. The cliffs have different heights. Sometimes the ball is thrown with a velocity of v, as represented by an arrow in the figures below. In case A, the ball is simply dropped and there is no arrow in the figure. Rank the speed of the baseballs just before they hit the ground at the bottom of each cliff. Okay, so we want to know this student drops theirs, these. This one throws theirs down, this one throws theirs up, this one throws theirs up. They're all throwing them at the same constant velocity v. We want to know when they hit the bottom down here, rank the speed. Okay?
And there should probably be a fence at the edge of the cliff because that student's starting to worry me the way he's leaning over.
It's all right. Stick figures it's a massless stick figure of science. So when they hit the ground, no forces. It's all right.
Well, if we learn nothing from the Roadrunner, it's if you don't look down, you're fine.
That's right. As long as you don't look down, gravity doesn't take effect. We learned that from the Roadrunner.
You know how I spent my Saturday mornings when I was, well,
you and me
high
both.
school and, well, yeah.
All right, type your answer in the chat.
At least for the ranking part.
Yes, type the ranking in the chat. All right, we got a wide array of answers because the questions are getting a little deeper. Okay, I'll give you a hint. When student C throws theirs straight up, it's going to go up, it's going to stop, and when it comes back down and it's back right at the same height, how fast is it going? Remember that this motion up and back down is symmetrical, right? So if I throw a ball in the air at 100 miles an hour, as long as there's no air resistance, It's going to go up, stop, and when it comes back down and I catch it, it's going to go 100 miles an hour. So that means that C is really identical to B, right? Because it goes up, comes back down, and then it turns into case B. All right? I think everybody has got C and D as the highest, which is good because they're higher up, and therefore they'll pick up more speed, more time or distance to accelerate. Okay, what about A and D? Okay, so this one's going to go up, come back down, and when it gets here, it's going to be like they threw the ball down. So it should be going faster than this one, right? So here we go. B and C should be the same. And then D should be next, and A should be the last. Okay? Okay, the ball's thrown from the high cliff will hit the ground with a greater velocity because they have further to fall. So like these up here, they have more time or distance to fall. So they're gonna accelerate more. But C is gonna go up, come back down, and then it'll be going downward. So it's gonna end up going faster than A. All right? Okay. An engineer measured the velocity V of a remote controlled cart on a straight track at regular time intervals. The data are shown in the graph above. During which of the following time intervals did the cart return to its position at time equals 0? Okay, now this is typical of a question. In fact, this is an old AP question where they're going to give you experimental or real world data. Okay, it's all made up, but it's still supposedly real world data. So when you see stuff like this, you notice the line's going to be a little janky, all right, a little wobbly. That's okay. Just look at the net effect. This is a straight line. This is a flat line. This is another straight line, and this is a flat line. Okay, so think of it that way. All right, and then look at your axis. How do I find the position from this type of graph? Ooh, look at you already. B, 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 B. All right. Genius. Physics students are the best. The answer is C. Let's see how this works. Okay, because this is unexpected. So let's see. How do we find the position? Well, position is related to the displacement, right? If it starts at the origin, we can find the displacement by looking at this area here. So how much did it displace? Well, it displaced, I don't know. This is approximately, let's see, that's 1, 2, 3, 4, 5. So that's about 3. And this is, I just said it's about 1, okay? Just to make it simple. And so this area right here, when I do 1/2 base times height, is about 1.5 meters, okay? That means the object has moved forward 1.5 meters-ish. Okay, and then from 3 to 5, it doesn't go anywhere. All right, and then it goes backwards with a negative velocity. Okay, so I need negative 1.5 meters for it to get back to where it started. So if I go, so 5, 6, 7, 8, I look at this slope here. This slope looks to be roughly similar to this slope. It's not exactly the same, but it's roughly the same. So that means I would need another about roughly 3 seconds in order to get the same area over here as I have negative area as I had positive area, so that they cancel each other out and we're back to where we began. This was a challenging question. Tons of my students missed this question as well, okay? So don't feel bad about this one. Just be careful. For me, it's very helpful if you draw the lines on here like I did, just to kind of help you visualize what's going on, okay?
It seems like people have the right concept, but they need to be a little bit more precise in I guess, the measurements or interpreting the graph on that one.
Well, we can definitely tell it can't be A or D. So those get crossed off right away, okay? So it's between B and C. So you're in the ballpark, okay? And And one of the things I always tell my students is, especially on the wordy questions where they have like a statement down here for A, B, C, and D. When you look at those answers, it's really important for you to read the answer. And if something in it is incorrect, just cross through it like I've done here, so you don't bother ever looking at it again. Okay. So sometimes you can't find the correct answer, but you can eliminate the ones that cannot be correct. And then you have a good shot, an educated guess of getting the correct answer. All right. Because remember, everybody, you're not trying to get 100%. Okay. It's nearly impossible. In fact, I'll take the released exams when they come out. I never get 100%. I always miss a few. Okay. And they don't expect you to get them all right. In fact, you need about a 70. I always say, if you get 75%, you get a 5. If you get somewhere around 2/3 correct, so 67, 65%, you'll get a solid 4. If you get at least half the questions right, you're guaranteed to pass. Okay? So that means if there's one you don't know how to do, you skip it on the test. Skip it and then work the ones you know how to do. And then at the end, go back and make sure you answer everything as best as you can. All right? So all the multiple choice, if you've got 10 that you had no idea how to do with last 5 minutes, bubble them in. Okay? And there's no points off for getting it wrong, only earning points. And on the free response, any questions that you're like, I don't really know what to do, but I know I got objects colliding, so the momentum should be conserved. Then write down momentum is conserved, because that's one of the things they're looking for. Do you realize that momentum is conserved? You may not know how to go past that, but write down what you do know has to be true. Okay? And earn a few points here and there. Because the difference between a 3 and a 2 is just one more point. If you just get one more point, you'll move from a 2 to a 3. You know what I'm saying? So just try your best and try and earn as many points as you can. You don't need to get them all right. Okay, here's our next question. So again, this is like a representation of real world data. So it's got some squiggliness, some jaggedness to the data. The student sets an object oscillating on a spring, and they use a motion detector to measure the velocity of the object as a function of time. A portion of the data is shown above. Okay, so the first question is, what's the total change in the object's speed between 1 and 1.1 seconds? And then the acceleration of the object at time 0.7 seconds is most nearly equal to which of the following? Okay, so type your answer in the chat. All right. Looks like most of us are putting down B and D. Let's check. Genius. Very good. So even though the data looks squiggly and the graph is kind of gnarly looking, it's okay. The same rules apply. You're just looking at the difference in velocity. It's a velocity time graph. So you read it at these 2 points, calculate your answer, and then it's the slope, right? So in fact, I estimated the slope, but I didn't need to when I answered it. All right. I went too far. Okay. We have a few more. High school student throws a baseball horizontally from the edge of a cliff. The speed of the baseball and the height of the cliff is given in each Rank the time it takes the baseball to hit the ground at the bottom of each cliff. Assume that the ground down here at the bottom is all horizontal, okay? Now I see, all right, I see a lot of you putting B, C the same. That's correct, right? But why are you putting A and D the same? They're not the same height, right? There we go. D has to be greater than A. There you go. All right. So these two, the vertical motion of a baseball is independent of the horizontal motion, right? So we don't care at all what the horizontal velocity was. We're just looking at the vertical velocity. They all start with a 0 vertical velocity. So we'd get the same answer if you just dropped the ball from that height. And that makes the answer easy then. B and C would be the longest time to hit the ground, D would be next, and A would be the last. They all accelerate down with the same rate of gravity. And so the higher up they are, the longer it takes. Okay. High school student throws a baseball again. They've got a lot of baseballs. From the edge of different cliffs, the speed of the baseball and the height of the cliff is given. Rank the horizontal distance the ball travels before hitting the ground. So now we're concerned about this distance, okay, side to side. All right, now this one's a little harder because the distance it goes in the x direction depends on two things. It depends on the velocity in the x direction. Oh, first of all, remember in the x direction, there is no acceleration, okay? So there's assuming no air resistance. So it depends only on the velocity in the x direction, which remains the same, and the time it's in the air, okay? So by that argument, we know that B and C take the same time to hit the ground. Since B is going faster, B will be the greatest distance, okay? Now, if you compare C and D, they have the same velocity, but C's in the air longer. So we know B is greater than C, and we know C is greater than D, all right? But now comparing D and A is a little harder because they have different velocities and they have different heights, okay? So the deal is that the time that they're in the air, I don't know, let me derive it for you quick, all right? So let me show it to you. Okay, so when you have something and it's falling in the y direction, okay, we have x, I'm going to write it with y's. Y equals y naught plus b y naught t plus 1/2 g t squared, right? I'm going to call this the starting spot 0, and I'm going to call positive y down, okay? So if I do that, it starts at a 0 position with a 0 initial y velocity because they're all launched horizontally, right? So that means 1/2 gt squared, or the time it takes for it to hit the ground is 2 times the y distance that it started divided by g square root, okay? All right. Now, the x distance it travels, sorry, the x distance it travels is the x velocity times time. Okay? So if you look back at this right here, we can see that this one right here is 4 times higher, but half the velocity. So look what we get. If we make this height 4 times higher, then that'll give us a factor of 2 because the square root of 4 is 2. But it's going half the velocity. So that's half the velocity. So I get a 1/2 factor here. So I get a twice the time in the air, but half the velocity. So D and A go the same distance. That's a hard one. Okay. All right. Does that make sense? This proportionality over here? The College Board asks you many times to do this proportional reasoning thing. Tons of them on the multiple choice, okay? And a lot of times they'll ask you the question without these numbers. They'll just say, you know, the velocity at A was V and the height was H. And then they'll say over here at D, now you're going, the velocity is V divided by 2 and the height is now, you know, 4H, okay? So you have to do it in symbol form. So practice that a little bit. All right, last one. Then we're going to take a break. All the cannons in the figures are identical and all are aimed at the same angle of 35 degrees to the horizontal. The cannonballs are all the same size and shape, but the masses of the cannonballs as well as the speeds they leave the cannons are different. Now we're going to assume no air resistance, of course. So I want you to rank the horizontal distance the cannonballs travel, and then also rank the acceleration of the cannonballs when they reach their maximum heights. Okay? All right. Okay, let's do the acceleration one first because this is a question that points out a misconception. When an object is flying through the air, when it reaches the uppermost part, say you throw a ball straight up, at the top, it has to stop, at least for an instant, right? It doesn't like stop, pause, and then fall. So it goes up, it stops for an instant, but it doesn't stay there. It doesn't stay at a velocity of 0. Therefore, it still must be accelerating. A lot of times students will say when it gets to the top, the velocity is 0 and the acceleration is 0. If that were true, then what would happen is the ball would go up, stop, and stay there because it's no longer accelerating. So the velocity stays constant at 0. That means all ball sports would be terrible sports. You'd shoot a basketball towards the hoop, it would go up, and then it would just stop. Okay? So when you get to the top, gravity's still pulling on it, so it's still accelerating down. So they're all the same at G, downward, not 0. Okay? All right, and this second one, the deal is there's 2 reasons why A goes the farthest. First of all, the vertical velocity determines the time it's in the air. So the greater the vertical velocity, the more time it has to fly. Okay? Since they're all shot at the same angle, the ones with the greater velocity will have more hang time. And then the horizontal velocity times the time determines the distance. Okay, so not only does A go farther because it has a larger horizontal velocity, it stays in the air longer, so it goes even further. That makes sense. Okay, so B and C would be the smallest. This mass makes no difference as long as there's no air resistance. All right. And there we go. Do we have any questions on this one? This is our last one. You could, Trey, that's correct. You could use the range formula if you want, but the range formula is not given on the equation sheet. So you don't really need it. When they say justify your answer, they want you to justify using words, but you can use equations to back up your statement, if that makes sense, okay? But you can't just work out a bunch of math to show that A goes the farthest. You have to use your words, and they're expecting you to use physics language, right? So a lot of times physics language, or not a lot of times, physics language does not come naturally to anybody. So you can write out your words and then like put an equation or a graph or a picture or whatever to help clarify your words, okay, to help you out because they're looking for understanding, okay? All right, great question. Okay, that is the end of our first session. So let's take, what time is it? Ooh, right on time. Why don't we take a 5-minute break and then we'll come back and then we'll do some forces. All right, Lou, do you have anything to tell them before we go?
That sounds great. I'm going to pause the recording so we miss some dead air, and we'll start up in about 5 minutes. So leave your, take a break and get something to drink.
All right, you're all doing great. See you in a bit.
Okay, welcome back for hour number 2. And this will be Chris again going over not just how things move, which we would normally call kinematics, but why they move. And in a post-Galilean what am I looking for? The word paradigm. We're going to say not why they move, but why they change their motion. So,
yeah.
Chris, take it away, please.
All right, here we go. Let's get started. So here's our first question. Again, we're going to type our answers in the chat. Let me get the chat up so I can see it. Excellent. And sorry, I'm just rearranging my screen over here. Here we go. All right, so now I can see the chat. Welcome back, everybody. Thank you for participating. You're doing fantastic, by the way. So just wanted to congratulate you all on that. So here's our first question. Various packages with different masses are moving on a constant speed conveyor belt. At the instant shown below, all the packages have the same constant velocity of 2 meters per second directed to the right. The packages do not slip on the belt. All the masses are given in terms of m, the mass of the smallest package. Okay, your question. Rank the magnitude of the net force on each package. Ooh, that's a bold statement, Matthew, that they're all 0. Why do you say that? There you go. Constant velocity implies no acceleration. And the big thing in forces, Newton's 3 laws, right? So actually, I tell my students it's Newton's 2 laws. Okay, the first one is really the third law. No forces can act. An object cannot apply a force on itself. It has to interact with another object. And when it does, the interaction between those two objects always produces equal and opposite forces. So one gets pushed to the right, one gets pushed to the left with the same force in opposite directions, always, always, no matter what the circumstances. Okay? So anytime you touch anything, it touches you back with the same force. Okay? So that's Newton's third law. And then really, we have Newton's law of, well, forces. It's really the second and the first one combined. Let me share my screen so you can see it. Okay? So force from 1 on 2 equals force from 2 on 1. That's Newton's third law. So whenever the objects, whatever they are, okay, force on one, force on the other, they're always the same, but in opposite directions, okay? And then the other one is really this law. You'll see it on the equation sheet written like this. The sum of the forces over m equals a, okay? Now, most books now, and teachers write it this way just because we're lazy and we don't like the fraction. But technically, this is the correct way to write it. That's the way it's on the equation sheet. The acceleration is proportional to the net force, and the acceleration is inversely proportional to the mass, which means that if there's a net force, the object will accelerate in the same direction. And if you double the force, you'll double the acceleration. Okay, if you cut the force in half, you'll half the acceleration because they're directly proportional. The mass fights this acceleration. We don't really know why. I mean, that's a really deep question in science of why there is mass. Why does it fight this motion, right? Newton said for an object in motion stays in motion, object at rest stays in rest, and it's because of this inertia, and inertia is measured by mass, okay? But it's a really deep question, quite frankly. So the deal is, if you write it this way, if the net force is 0, then the acceleration must equal 0. And there are two ways that this can happen. The acceleration could be a velocity of 0 or the velocity is constant. Okay? So anytime you're looking for these words, because all of this stuff goes together. This is equilibrium. Okay? So if it's moving at a constant velocity, it's in dynamic equilibrium. There's no acceleration. Forces all cancel out. If it's sitting still, it's in static equilibrium. There's no acceleration, and the forces all cancel out. So if you see any of these things, they all imply the whole set. So if it's not accelerating, you know it's one of these two, and the forces cancel. If you know the forces cancel, you know it's not accelerating, and it's one of these two. Okay? So that goes in a big, big lump concept. Okay? And what we have in this particular case is that's all lumped together. They're moving at a constant velocity. So you could have stopped right here. Constant velocity, oh, net force, all 0. Okay? Awesome. Okay, how about this one? The spring is attached to the ceiling of an elevator and a block of mass m is suspended from the spring, because this is what we do in elevators because we're physics people. The cases are identical except that in case A, the elevator is moving upward at a constant speed of 7 meters per second. And in case B, the elevator is moving downward at a constant speed of 9 meters per second. Will the spring be stretched more in case A or B, or will they stretch the same? Type your answer in the chat. So far we have A greater than B, or it stretches more in A than in B. Oh, everybody's putting that. Okay. Now, listen carefully.
Oop, we have a
Are
dissenting
these
voice.
objects accelerating? Constant velocity, right? So what does that tell you about the forces? The net force has to be 0. Now, what are the forces acting? Well, there's a gravity force down and a spring force up. And they both have the same mass, so they have the same gravity force. So that means the spring force up has to be the same, which means that they have to stretch the same amount. Okay? So they're in dynamic equilibrium, no acceleration, forces cancel out. The spring force has to equal the gravity force, and the gravity force is the same in both cases. So therefore, the spring has to stretch the same in both. Yikes. This was unexpected, right? Because our brain tells us, hey, when it's going up, it stretches more. Okay, but if it's accelerating up, it stretches more. Okay, than if it's accelerating down. So this was a great question. Okay, so just remember, look for that constant velocity thing. And then always draw a quick free body diagram, even if it doesn't ask you to. Even if it's a free response problem and they don't ask you to draw one in your answer. Because I'll tell you, sometimes you get points for it because it helps explain what you're thinking. And then the reader of the test can say, oh, they're on the right track. They get this point. Okay? So always draw one. So I always tell my students to do this, so that whenever you have any problem at all that has to do with forces, step number 1 is to draw a free body diagram, okay? And you just make it simple. You know, there's the center of mass of the object. You got a force, you got a force. Always make your forces point away. Try to point them in the right direction. Try to draw them to the right length, okay? And then step number 2, always ask yourself, is it accelerating? Because that tells you, yes, well then F equals ma, and there will be a net force. And if the answer is no, then the sum of the forces is 0. So no net force. And all the forces cancel out. That's huge. Many of the questions on the test can be answered correctly if you just ask yourself that when you're looking at forces, okay? And then step number 3 is you set up a coordinate system. Oops, I can't write it. Now this is for if you're trying to set up an equation. You need to set up a coordinate system, okay? And that works like this. And here's why this is important. So if we have an object that, say, is accelerating this way on a horizontal surface, then it makes perfect sense to set up an x, y coordinate system, okay? And this is great because in the x direction, you're accelerating. So the sum of the forces in the x direction would equal ma in the x direction, okay? But in the y direction, notice there's no part of the acceleration in the y direction. So in the y direction, all the forces have to cancel out. That's a big deal, okay? Now, what if we're on an incline? So we have an object like this. Well, then what we would do, we would have forces on this. We would have, like, say, gravity. We would have a normal force. And we would have, say, a friction force, okay? But is it accelerating? Well, if it's accelerating, it's only going to accelerate either up or down the incline, right? okay, depending on these forces. So let's say that it's accelerating down the incline. Now notice I don't draw my acceleration on my free body diagram. Never, ever, ever on the AP test. When you draw a force diagram, only draw the forces, no velocities, no accelerations, and never draw components. Just draw the forces, and that's it. If you need another drawing to help you solve it, draw it off to the side. Okay? If they ask you to draw a free body diagram. Now, in this case, we would want to set up our coordinate system this way. Okay? Parallel and perpendicular to the acceleration. That's actually what we did here. This is parallel and that's perpendicular. And the reason why this is important is in the parallel direction, we were always going to get F equals ma in the parallel direction to the acceleration. But in the perpendicular direction, none of this acceleration is in that direction. So we would always get F equals 0. So in this direction, the forces all cancel. But in this direction, F equals ma. Okay? It makes the math simpler. And one last example. Okay? Say you have a ball on the end of a string and it's going around a circle like this. So you have around here we have Six Flags and amusement park, and they have the swing ride where they got this big tall pole and they got a cable like this and you swing around it, right? Does that make sense? Kind of like, bocce? No, it's not bocce ball, tetherball, okay? All right, so draw your free body diagram. Well, here's the ball. There's a gravity force down and there's a tension force this way. Now ask yourself, is it accelerating? And the answer is yes, because it's changing direction, okay? And so which way is it accelerating? Well, it's accelerating towards the center of the circle. Acceleration towards the center, A sub C, okay? So which way should I set up my coordinate system? Always parallel and perpendicular to the acceleration. So your coordinate system would look like this. One parallel to the acceleration, one perpendicular to the acceleration. Okay? Yeah, I do actually have a YouTube channel for my students from last year. If you want, at the end, I can give it to you. It was for my students because, we were all locked out at the end in spring. So it's some review stuff. Some of it's kind of boring, but it goes through most of mechanics anyway. All right, so here's the deal. That means that I would split my forces up like this, right? And so this upward part of the tension must cancel this downward part because they're not accelerating up or down. And this horizontal part, then I'm going to call it T sub X, okay? It's the sum of the forces in the parallel direction equals MA. And so this would be Tx would equal M, and you're accelerating towards the center, right? That makes sense? Hopefully you can see that. Sorry. Would it be better if I turn that light off? I don't know. Let's go with it. All right? So there you go. So here's the deal. Whenever you're doing F equals ma or any kind of forces at all, draw a quick free body diagram. Ask yourself if it's accelerating, because that tells you huge amounts of information. And then set up your coordinate system so it matches your acceleration, so that if you have to write these equations, it's going to be much easier, right? So step number 4 would be set up or write your F equals ma for the 2 directions. Okay, so your parallel and perpendicular direction, okay? If you need to. Sometimes you don't need to do that. All right? Does that help everybody? Do you have any questions on this idea? Because they're going to ask you, they're going to set you up with these questions like I just gave you. And they're looking to see, do you understand that these forces are canceling out or not? Okay. So always look for that keyword, constant speed or constant. Okay, be careful. Constant speed, since you're only going up and down, there's no acceleration. But like a planet going around the sun, it's going at a constant speed if it's in a circle, but it is accelerating because it's changing direction. So they're going to ask you questions. Do you understand if you change speed, you're accelerating? And they're going to ask you questions. Do you understand if you change direction, whether you're accelerating? In both cases, you need a net force to change direction or to change speed. Okay? There's a lot of stuff. I applaud you for taking physics because it hurts your brain a little bit, right? It makes you question everything that you've thought about how the world works. Okay? But you're getting so much smarter. You're doing awesome. Okay, here we go, everybody. Here's our next question. A student pushes horizontally on two blocks, which are moving to the right. Block A has more mass than block B. There is friction between the blocks and the table. For the situation where the blocks are moving at a constant speed, which of the following statements is true about the magnitude of the forces? Okay, and I'm going to let you read those and which one is correct. Which one is correct and why? Okay, type that in the chat. All right, excellent. Okay, you were not fooled. Good. Okay, the idea is this Newton's third law idea, that they're pushing on each other, so the force has to be the same, period, end of question. So you can justify that on the test when they ask you, like, how these forces compare or whatever, and then they ask you to explain your answer. You can just invoke Newton's third law. And if you forget that it's Newton's third law, just write forces are equal and opposite. You'll remember that, okay? Or forces come in equal and opposite pairs or something like that, all right? I had a student one time that were like, he was really worried because he's trying to justify the answer. And he wrote, it's one of Newton's laws. I can't remember if it's Newton's first, second, or third law. Please don't count this wrong. And then he went on to explain that it was equal and opposite forces. That's all you need. Just explain equal and opposite. All right, here we go. These graphs are the net force versus acceleration for different objects. All graphs have the same scale for each representative axis. Okay, rank the mass of the object. So there's a force on the object and it accelerates. And this is the graph, a function of force versus acceleration. Rank the masses. Okay, you're either putting C, A, B, D, or you're putting the opposite. Okay, so let's see and think about this. There's a couple of ways to answer this. Okay, if you just pick a force, like halfway here, pick a force and go across and then down and read the acceleration. Okay, pick a force. And so, hey, this one right here, it takes very little force to accelerate it, so it must have a small mass. okay? Or C, it takes a whole lot of force and you don't get a lot of acceleration, so it must have a very large mass, okay? Another way to think about it would be to remember that F equals ma, okay? And we're graphing F versus A, right? And we're getting a line. So look, y equals mx plus b. If I graph F on the y-axis and I graph acceleration on the x-axis, hey, look, the slope m must be the mass m because it's linear. Okay, so all you got to do is look at the slope, and the one with the highest slope has to have the highest mass. Okay, so there you go. All right, next one. This looks vaguely familiar. Two identical springs are attached to the ceiling of two identical elevators with a block of mass m attached at the bottom of the spring. Elevator 1 is moving upward with a velocity of 5 meters per second and accelerating upward at 3 meters per second squared. Elevator 2 is moving downward with a velocity of 8 meters per second and is accelerating upward at 3 meters per second squared. Will the spring be stretched more in elevator 1, 2, or will they stretch the same? Type your answer in the chat. Outstanding. Very good, everybody. Do we care about the velocity at all? No, velocity is not related to forces, period. It's related to acceleration. So we don't care if it's going up or down. All we care is the acceleration. They have the same acceleration, so therefore they'll have the same exact stretch. Nicely done. Nicely done indeed. Okay, next one. A student pulls a box across a rough floor at a constant speed with a force of F at an upward angle. The force diagram representing the directions of all the forces is shown. The student makes the following statement. All the forces on the box add up to 0. That means the normal force equals the weight, and the force of friction equals the force pulling the box along. Okay, so what parts of this statement are correct, if any, and what parts of this statement are incorrect, if any? All right, careful. Is normal force actually equal to weight? Okay, we got a lot of stuff going on here. So first of all, here's our free body diagram. If you look at X and Y, notice that we have two forces in the X. There's an X component for the pulling force and the friction force. And in the Y direction, we actually have 3. Okay, we have the normal force up, and part of this pulling force is up, and then a gravity force down. Now, it's moving at a constant speed. That means all the forces cancel out. Okay, so that part of the statement is correct. However, the incorrect part is the normal force is not the only force up canceling gravity. There's actually part of the pulling force. Okay, so what we would get is friction would equal the horizontal component of the pulling force, and gravity would equal the normal force and the upward part of the pulling force, okay? All right, be careful. Don't assume that normal force equals mg or gravity force all the time. Like in an elevator, when you're accelerating up, normal force is bigger than gravity. When you're accelerating down, normal force is smaller than gravity. So it's only going to be the same as gravity if you're on a horizontal surface and you're not accelerating up and down. Okay? Okay, I love this problem because it's got a couple of layers to it. Okay? In both cases below, Grace pulls the same large crate across the floor at a constant speed of 1.48 meters per second. Is the magnitude of the force exerted by Grace on the rope greater in case A, greater in case B, or the same in both cases? All right. Looks like we're getting a consensus of greater in case B. That is correct. But there's more than one reason why. All right, so let's go through it. So it's definitely greater in case B. Okay, now the first thing is the crate is moving at a constant velocity. That means the forces cancel out. That means there has to be friction. Do you see why? If Grace is pulling to the right and there's no friction, then the crate would accelerate to the right because there'd be nothing backwards to cancel out the forward force because we have to have a net force of 0. So there has to be friction. That's key. Now in case B, most of you will easily get that the fact that she's pulling at a bad angle, right? So only her horizontal part is pulling it forward. So this is a wrong way to pull this thing, right? She's wasting some of her force because she's pulling downward. Now, the thing is, though, it's a double whammy. Since she's pulling down, she's increasing the force down on the crate. Gravity's pulling it down, and she's pulling it down. That increases the normal force. And since there's friction, that means friction is going to be bigger. So she not only pulls at the wrong angle, she's increasing the normal force, which is increasing the friction, which is making it even harder for her to pull it forward. So at least she should have pulled up on the crate, because then at least she'd lower the friction force, right? Which would help a little, but probably would still make it a bad call. Okay? So this one would be a great one of those kind of like a paragraph argument questions, because there's several places to award points, okay? So I'm sure your teacher has given you one of these paragraph argument problems where it says in a clear, concise paragraph, explain or whatever, right? And it just gives you a bunch of blank space. Okay, what they're looking for in these questions is the correct answer, and then for you to apply physics, like this idea of constant velocity, forces cancel out. You know, that means there must be friction. And there's usually, these are 5-point questions. 1 point is for a logical argument, okay, that addresses the question. So there's usually 4 physics points, okay? So whenever you see one of those paragraph ones, think about what are the big 4 ideas, okay, that you have to explain. So there's probably going to be 4 of them, somewhere around 4. And if you only get 2 or 3, that's better than none, right? So remember, you're just trying to get at least half the points or better to pass, okay, to get a 3 or 4 or 5. Hey, look, we've seen this graph before. Figure at the right shows a vertical velocity of an elevator as a function of time. I want you to do a couple of things. You can just do this on your paper. You don't have to type this in the chat. What does a free body diagram look like for the elevator at 6 seconds, 4 seconds, and 12 seconds? Now, let's just do the elevator as a whole. So you have the elevator and then the forces on the elevator, okay? And then at what times would the bathroom scale read your actual weight? So let's say that you're in the elevator and you're standing on a bathroom scale. At what times will it read your actual weight? And then the last question is, what's the normal force on a 80 kilogram person at 22 seconds, okay? So I'll work out that last one with you, but see if you can answer questions A and B. Okay. So free body diagrams, hopefully you're getting really good at these and you can sketch them really quickly, okay? Remember, it's just a simple picture. In fact, you can just draw a center of mass symbol if you want. That's all you really need. Unless when you get to rotation and rotational motion, it'll be important to draw the figure to the right shape because where the forces are attached to the object will make a difference for whether it will spin or not, okay? But we'll leave that for later in the year. All right, so here, for the first 6 seconds, at 6 seconds, you're accelerating up. So tension on the elevator must be greater than the gravity force on the elevator. At 14 seconds, you're not accelerating, so the forces must cancel. And at 22 seconds, the elevator is accelerating down, so the tension in the cable must be less than the gravity force. Many times on the test, they'll ask you to draw these to scale, and they'll put a little grid, and we'll have another one like that in just a minute. Now, the bathroom scale then will only read your actual weight when you're not accelerating because it doesn't have to push up extra during the upward acceleration or less when the downward acceleration. Okay, so only during the 10 to 18 second range in the middle. And then the last part is, this is the equation for this 22 seconds. So that's why I got this little arrow here. So the normal force would be up on you when you stand on a bathroom scale from the bathroom scale, and then the gravity force is down. And that has to equal ma. And since you're accelerating down with a negative acceleration, you're going to end up with the normal force being less than your actual weight. At my school, I've got an elevator. And so we always I got about 5 or 6 bathroom scales. We go over to the elevator and put them on the floor, and then we hit the up button and the down button, and we would just watch what our weight does. And you can see this on a real elevator, and you can feel it. When the elevator starts to go up, you get that kind of funny feeling in your stomach. And when it starts to slow down, you get that funny feeling in your stomach, okay? And all the rides at an amusement park, almost all of them, are this acceleration thing, because that's where it's the most fun because you got extra forces on you. Okay, this one's got a lot of words. Let me read it to you. 2 blocks are released from a device at time equals 0 from the same height h. Block A has a mass of 2m, while block B is a smaller mass of mass m. Block A has no initial velocity and falls straight down. So the device drops A straight down, while it gives B an initial horizontal velocity of V naught. So it gets shot to the side, and it travels a horizontal distance D before striking the ground. The blocks reach the ground at the same time, TF. And we know that from what we just talked about in the last hour, is they have the same vertical velocity of 0 to start, so they're going to hit the ground at the same time. Now, here's the question. Block A lands on a force sensor. So there's a force sensor down here, which is placed on the floor. The force sensor records data shown at the right in a clear, coherent paragraph length response. Explain why the graph of the force sensor has this shape. Include explanations for each key feature of the graph. So I gave my students a hint. There are 3 distinct features of the graph. This before it hits the ground, the time when it hits the ground, and then the time after it hits the ground. Okay? I want you to think about it for a second. Why would the force sensor read this at the beginning, and then this at TF, and then this after it's hit the ground? Okay? So think of it as before, during, and after block A hits the ground. Okay. So why does it read 0? Well, it hasn't hit the ground yet, right? So it should read 0 for the force sensor. Okay. Okay. And then why does it read this constant value after it's hit the ground? Well, it should be reading the weight of this block, right? Because it's hit, it's stopped. And so the force sensor should be reading the gravity force, right? Gravity's down and it has to push up with the normal force. So the normal force equals the gravity force. In fact, this value right here should be mg, the mass of the block. Actually, it should read 2 mg because it's a mass of 2m. Okay, so here's the hardest part. Why do we get this spike in force? A lot of times students will say, well, because it hit the ground. Okay, but why? Why do we get the spike in force? So our answer is right here. This is worth 3 points on the test I gave my students. For realizing that this large spike in the force at TF is because the normal force, or the force from the force sensor, is larger than the weight of the block, because the block is moving downward and the force sensor must stop it by giving it an acceleration upward. Does that make sense? So this is just like the elevator, really. That block is descending down and the floor has to push up to stop it, and it has to push up with more than the weight, because otherwise it would just fall at a constant rate, right? You keep falling. We don't want that. It would burrow through the floor. So it has to have this spike in force to push up, to slow the block down, to rest. Okay? So there you go. Okay, next part of the question. Now let's look at block B. Block B lands on the floor without bouncing, so it's a non-bouncy floor of science. Okay, after landing on the floor with a horizontal velocity of V naught, still the same horizontal velocity, the block slides to the right a distance x, as shown in the figure, before stopping. So it comes down like this, and it slides right here. Okay, derive an algebraic expression that could be used to determine the coefficient of friction from the given quantities and any constants like g. All right, see if you can do that real quick. I'm going to give you a minute or so. Okay, we're running a little tight on time, so I'm going to go ahead and jump in here, okay? So let me show you my screen. So let me ask you a question. Oop, that looks a little blurry. Hang on a second. Did you draw a free body diagram, even though it didn't ask you to? Did you decide whether it was accelerating or not? Okay, and did you set up your coordinate system? Okay, so we're looking for mu. Okay, the only way for us to find that is to use this equation. Force friction equals mu force normal. And it's kinetic friction technically, right? Because it's sliding. Okay, so I got forces going on. So let me draw a free body diagram. I've got a gravity force down, which is mg, or force of gravity. I got a normal force up, and I have a friction force to the left. And let's see, is it accelerating? The answer is yes, it's accelerating to the left. Therefore, I'm going to set up my coordinate system. Since it's moving to the right, I'm just going to set up a standard XY because X is parallel to the acceleration. All right. Now, that tells me that these two must cancel, and that's causing my acceleration. Okay. All right. So I now have this, it's going to be mg, right? So I got that part. And this I'm going to find from F equals ma, where this is the force friction kinetic equals ma. And my block is actually capital M, right? So I need to find A, the acceleration. So now I've got to figure out kinematics. All right, x naught x, v naught v, a and t. My block starts here and moves to the right. It stops over here. It has an initial velocity. So I'm going to call this 0. So it starts at 0. It slides a distance of x. Nice. Starts with an initial velocity of v. It ends with a velocity of 0. We don't know the time. So that tells me I got to use v squared equals v naught squared plus 2a x minus x naught. Okay. Since I don't know the time, I have to use this one. All right. So get rid of your zeros. So that's 0 and that's 0. So I have 0 equals V naught squared plus 2AX. Solve for A. So A equals V naught negative V naught squared over 2x, right? And that makes sense that it's negative, right? Because my force is to the left, so that's going to be okay. So my force is actually to the left, and my acceleration is to the left. So my negative force of friction equals m times V naught squared over 2x. Did I do my math right? Yeah. Okay? So now I just got to put all this crud together. So I end up with this m V naught squared over 2x equals the kinetic coefficient of friction times mg, and my m cancels. And so the coefficient of friction equals V naught squared over 2xg. All right? Now, how would they grade that on the test? Okay? So what they would be looking for in this one is that you can solve it symbolically, right? But they would be looking for points like this. Here's it all listed out, same thing. All right? So for attempting to use kinematics to solve for the acceleration of the block, because you need to realize you got to find the acceleration. Okay? And that's the acceleration. Sometimes they'll require you to actually write down the correct one to get this point. But for using kinematics, and then for using Newton's second law to solve for the force of friction, okay? And then for the correct value of the coefficient of friction. Okay, that's generally kind of the way the points are awarded. Sometimes it's a little different, but look what they're looking for. Are you using kinematics to find acceleration? Are you using Newton's second law? Are you setting it up correctly to solve it? Okay? This is very common on the test where it requires, say, like you might have to use forces and then kinematics, or kinematics and forces, or kinematics and momentum, or a lot of times momentum and energy, if you've gotten that far in your class yet. So just be aware that it's probably not going to be just a single concept question, okay? All right, and I have one last thing real quick, and then we'll quit. There are a couple of more questions in the PowerPoint. I think Mr. Akampora can probably give you the link to those, and they have the key with them. I'll show you them really quick at the end, and I'll also give him the link to the YouTube channel for AP Physics 1 and AP Physics 2 in case you take that. In case you want to watch any videos, they were made for my class, so they may or may not be helpful to you, but they're kind of, I tried to make them as review for mechanics, okay? All right, so in this one, the last question is, the dots represent blocks A and B. Draw a free body diagram showing and labeling the forces, no components, exerted on each block after both blocks have come to rest. So they're here sitting on the ground. What would that free body diagram look like? Notice they've given you grid lines. That means you better draw them to the correct appropriate length, proportionally speaking, okay? All right, because I don't want to steal any more of your Saturday time. Here we go. Now, always draw your arrows pointing away from the dot or the object. Always have your arrowhead go directly to one of these lines. They're always made so that you can draw them so they line up with the lines exactly. They're looking for two things in this one. normal force and gravity have to be equal to each other or cancel in both free body diagram. And they're wanting to see, did you realize that the gravity force for block A is twice as big as B? So I drew mine 2 down on B, so I have to draw this one 4 down on A. Could you have drawn this one on the right 1 down? Yes. Then this one on the left would be 2 down. Okay? Don't draw it 1.5, people. It just makes it hard for the reader, and they might count it wrong because they see it differently than you do. Draw it directly to one of these dashes, okay? And there you go. I got another question here with a tilted coordinate system and a couple of questions, and there's the key, and then one of these pulley system things, and there's the answer to that one, okay? So we just missed a couple of questions, all right? And then Mr. Akampora has the both of these PowerPoints, and I'll give him the link to the YouTube channels as well. Everybody, congratulations, you did awesome. You're fantastic students. Good luck on the test, and I will also be presenting at your next Saturday content review session in a month, the first Saturday in February.
Mm-hmm. And I do
So I
have,
hope to see you there.
and those notes are already posted on the Advanced Kentucky webpage. Thank you, Chris, and I will get the information out. So thank you, students and teachers, and enjoy the rest of your Saturday. Stay safe.
Have a great Saturday, everybody. See ya.
Bye now.